loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. It introduces a fundamental paradox. If all that we see and experience originated from a single point of infinite density and temperature, how do we account for the presence of that singularity in the first place? The notion that everything, matter, energy, time, and space, emerged from a void challenges our basic philosophical and scientific principles. In addition, research from the James Webb Space Telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. These revelations are reshaping our cosmic narratives and forcing experts to revisit long-held beliefs. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and attempt to answer this question and many more. With curiosity as our guide, we venture into the deepest recesses of time and space, uncovering clues that may redefine our understanding of existence itself. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel. Hit the like button, share this video to reach more people, and turn on the notification bell so you never miss a cosmic update. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is now. Approximately 13.8 billion years ago, all that we know, the stars, planets, atoms, and even the forces of nature, was compressed into a single, incredibly dense point. During that period, all the elements that make up our world were formed in a matter of minutes. It's a breathtaking idea, one that suggests that the chemical fingerprints of our world, the carbon in our bodies, the oxygen we breathe, the iron in our blood, originated from that primordial event. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an extremely high temperature of over quadrillion degrees. At such mind-boggling heat and density, conventional matter could not exist as we know it. Quarks and gluons swirled in a fiery plasma, bound only by the laws of quantum physics. Interestingly, this astonishing narrative aligns consistently with all current observations. Measurements of cosmic microwave background radiation, the lightest elements such as hydrogen and helium, and the large-scale structure of the cosmos all match what the Big Bang model predicts. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements, and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this description fits the reality of our universe perfectly. The mathematical models work, and the observational evidence is compelling. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the very first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. General relativity explains the behavior of gravity on a cosmic scale, while quantum field theory governs the microscopic world. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point at which our current methods cannot provide meaningful solutions. One of the indications of this difficulty is the existence of a singularity, a point of infinite density, at the beginning of the Big Bang. This notion suggests, quite literally, that the universe was once compressed into an infinitely small and dense state, which seems to be absurd. It defies logic and suggests that our theories are breaking down. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provide a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge. So, we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Unlike point particles, string theory suggests that fundamental particles are actually tiny vibrating strings. The different vibrational modes correspond to different particles, and through this unifying principle, gravity and quantum mechanics can coexist in the same theoretical framework. Within string theory arises the concept of an ekpyrotic universe, which takes its name from the Greek word meaning conflagration or fire. This idea suggests that the Big Bang as we know it was the result of an earlier event, implying that it was not the absolute beginning, but rather part of an ongoing process. Extending the notion of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains, almost imperceptibly, after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photons in a vast void. The universe emerges from what, from another point of view, essentially approaches nothingness. Although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one, the mystery lies in how the same state can be interpreted as both a cold, empty universe and a dense, hot universe depending on the point of view. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the cold, empty state and the hot, dense state can be connected through the scale transformation, aligning their spatiotemporal structures. Despite their differences in size, they can be identical in essence. Penrose argues that the concept of size loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old, cold state to a young, hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time. Since in these extreme states, both size and time lose their conventional meanings, the cold empty state and the hot dense state exist on separate timelines. This means that from the perspective of an observer within his own time frame, the cold empty state would continue